Let's talk about how to factor a quadratic. It's arguably one of the most important skills that you learn in Algebra 1 that carries with you through the rest of your math classes. So starting with x squared plus 10x plus 16, what we're basically doing is the opposite of the distributive property. So in today's lesson, most of these will be trinomials. Not all of them, we'll get to some exceptions, and we're going to factor them into two binomials. To do that, let's think of what times what is x squared. Well, that's x times x. Then what we're going to do is we're going to come up with two numbers that multiply to 16 and add to 10. So because we want them to multiply to be a positive number, we know the signs in our parentheses need to match. They're either going to be plus plus or minus minus. And because they're adding to positive 10, they're going to be plus and plus. So we're looking for two positive numbers that multiply to 16 and add to 10. And those two numbers are 2 and 8. 2 times 8 is 16. 2 plus 8 is 10. So this is the factored form of this original quadratic expression. They mean the same thing. If I were to distribute this back out, x times x is x squared, x times 8 is 8x, 2 times x is 2x, and 2 times 8 is 16. Combining like terms, we get a 10x in the middle, and we're back to where we started. So this is the factored version. The other one is the standard form. They both represent the same quadratic expression. We'll move through the next several a lot faster. The next example is very, very similar. It's a trinomial, so we're going to start by trying to factor it into two binomials. M times m is m squared, and we're looking for two numbers that multiply to positive 12. And they're going to add to negative 8. We know those two numbers need to both be negative if they're multiplying to get a positive number and adding to get a negative number. And 6 times 2 is 12. 6 plus 2 is 8. So our factors are negative 6 and negative 2. It does not matter what order you write the factors in. M minus 6 times m minus 2 is the same thing as m minus 2 times m minus 6. Next one. We're looking for two numbers that multiply to 3, add to negative 4. Again, they're both going to be negative, and the only two numbers that multiply to 3 are 3 and 1. And those add to 4, so it works. Not every quadratic expression will be factorable. They will be in this video, but if you ever run across a quadratic that is not factorable, we just call that prime, as in we cannot factor it any further than what it looks. In the next example, we're multiplying to get a negative number, which means negative 21 is what we're trying to get. And so that means that our signs are going to be opposites of each other. We need a positive number times a negative number if we're going to multiply to get negative 21. Since we're adding to get 4, I know the bigger of the two numbers needs to be positive. The good guys win. They add to get a positive number. And those two numbers would be 7 and negative 3. Try the next two. Pause the video and try them. The next one, we get c minus 5 and c plus 3. And the last one, we get z plus 15 and c minus 2. This one is a little trickier. But if you ever get stuck, just start making a list of numbers that multiply to get that last constant. So the numbers that multiply to get 30 are 1 and 30, 2 and 15, 3 and 10, 4 and nothing, 5 and 6. And then just keep going like that. We know one needs to be positive and one needs to be negative, so just try. Takes some trial and error, but you'll always get to the answer if you just start at the beginning and go from there. All right, in all those examples, there was no leading coefficient, but now there is going to be a leading coefficient, or in other words, a number in front of the x squared term. When there's a number in front, or just in general with factoring, we always need to check for a GCF before we start factoring. GCF stands for greatest common factor. Is there a number that all of those terms, number or variable even, that all those terms can be divided by? In this case, all three of these terms can be evenly divided by 4. So because our GCF is 4, we're going to start by taking a 4 out of each one of those terms, or dividing each term by 4. So like I mentioned before, factoring is the opposite of the distributive property. So basically, if you were to distribute that 4 back out, you would get what you started with, 4x squared plus 8x minus 60. Now we're going to look at what's in the parentheses, and we're going to try factoring that into 2 binomials, just like we did before. X times x is x squared. We're looking for 2 numbers that multiply to negative 15. So we know one's positive and one's negative, and add to 2. That needs to be a positive 5 and a negative 3. In our final answer, we do need to include that GCF of 4. The factored form, if you were to distribute it all out, should give you what you started with. So we need that 4 in front. The next example also has a GCF, a greatest common factor. All 3 of those terms can be divided by 3. So we're going to take a 3 out, or factor out a 3 from each one of these terms before we get started. Not only does it make your factoring life easier if you take out a GCF first, but your answer will not be entirely correct if you forget to take out that GCF. So always do that step first. Always check for a GCF. With what's left, we're going to factor that into 2 binomials, or try to. This time we're multiplying to positive 15, and they need to add to negative 8, the 2 numbers. So they both need to be negative, and those would be negative 3 and negative 5. Don't forget your GCF goes in front when there is a GCF. What if we have a leading coefficient, a number in front of the x squared term, or in this case, y squared term, but we can't, it's not a GCF. There's a number in front, but there's no GCF. What do we do? Well, how I teach this method that I've learned, often called the slip and slide method, is we take that number and we're going to multiply it by this number in the back. Basically, we're cheating. We didn't want that number in front, so we're going to multiply it by that back number so that we have a quadratic that looks like what we're used to factoring. This, we know how to factor. We cheated, but don't worry, we're going to uncheat later. 2 numbers that multiply to 24 and add to negative 14 are negative 12 and negative 2. Because we cheated by 3 in the beginning, we need to uncheat. We cheated by multiplying by 3, so we're going to uncheat by dividing by 3. We have to undo that step. 12 divided by 3 is 4, so this first factor becomes y minus 4. 2 divided by 3 is just 2/3, so when that happens, we're going to take that bottom number and we're going to move it up front. That's the slide and slip and slide. So that's going to become 3y minus 2. So remember, the factors that you end up with, if you were to multiply it all out, you should get back to what you started with. So if I take y times 3y, I get 3y squared, just like the first term up here. Y times negative 2 is negative 2y. Negative 4 times 3y is negative 12y. And negative 4 times negative 2 is positive 8. If you don't get what you started with, something went wrong, and you need to check it. In this case, we got what we started with. Another example, same idea. There's no GCF because that middle term just has an invisible 1 in front of it. So we're going to cheat by multiplying the 6 by the 12 to get rid of it. So we have x squared plus x minus 72. We're looking for two numbers that multiply to negative 72. So one positive, one negative number. And they need to add to 1. So that's going to be a positive 9 and a negative 8. Because we cheated by multiplying by 6, we're going to uncheat by dividing by 6. And neither one of these divide evenly. 9 divided by 6 doesn't come out nicely, and 8 divided by 6 doesn't come out nicely. But they can both be reduced. So let's do that. We get 3/2 and 4/3. If you forget to reduce at this step, and it can be reduced, you will not get the right answer. I'll show you why here in a second. They still don't divide evenly, so we're going to do that, move that bottom up front. So we have 2x plus 3 and 3x minus 4. Just doing a quick check, I want to make sure if I take 2x times 3x, do I get 6x squared? And I do. I can go ahead and multiply that out further, but at least multiplying those first terms together should give you a pretty good indication of whether or not you missed a step or not. If I would have tried to move the 6 up front earlier and got 6x plus 9 and 6x minus 8, if I would have tried to check by taking 6x times 6x, I would have gotten 36x squared, which is far larger than the first term we should have gotten. We know our first term needs to be 6x squared, not 36x squared. That's why it's crucial that we remember to reduce our fractions before we do that, that slip and slide. All right, a couple more steps just to put it all together. When your leading coefficient is negative, like it is on this first example, even if there is no other GCF, and this first example does not have any other GCF, we still need to take out a -1 before we start factoring. Before we factor, our first term needs to be positive. If it's not positive, like in this case, take a -1 out of each one of those terms so that it is positive. Now, with what's left in the parentheses, we're going to use that slip and slide method. We're going to take 4 times 5 to get -20 back there. So we're looking for two numbers that multiply to -20 and add to 8. We know that one's positive and one's negative, and it would be positive 10, -2. Because we multiplied by 4 when we slipped, now we need to divide by 4 to undo that step before we slide. Neither one of these divide evenly, but they both can be reduced. And that will always be the case. If neither one of them divide evenly, you can always reduce those fractions. So always check for that. So we get 2x plus 5 times 2x minus 1. And don't forget we took out a -1 in the beginning, so that needs to be part of our final answer. The GCF needs to be a part of your final answer. Another example, there is a GCF here, but it's not 8. It's 4. So because there's a GCF, we do still take that GCF out of each one of those terms. Then we do the slip and slide. So when there's a number in front, don't automatically slide it to the back. You need to take that GCF out first if there is one. It makes things easier for you, and your answer is not fully correct if you forget that step. So don't forget that step. All right, in this case, we're looking for two numbers that multiply to 18 and add to -9. That would be -3 and -6. We multiplied by 2, so now we need to divide by 2. So not the 8. We never slid the 8. We slid the 2. We cheated by multiplying by 2. Now we need to uncheat by dividing by 2. 6 divided by 2 comes out nicely. 3 divided by 2 doesn't, but we can rewrite that as 2c minus 3. And because there was a GCF, that needs to go in front. Let's look at a few special cases. The first is difference of squares. You'll notice for each one of these examples, we're missing the middle term. So let's pretend for a second that that middle term was there. And this said x squared plus 0x minus 25. So there's no x term, so we'll just put a 0x there. That means we're looking for two numbers that multiply to negative 25 and add to 0. That's positive 5 and negative 5. This is called a difference of squares problem. And here's the shortcut. If you have two perfect squares like x squared, the square root of x squared is x, 25, square root of 25 is 5. Those are both perfect squares. And they're separated by a minus sign, so difference of squares. We can set up two parentheses that look exactly the same, but one set is a positive factor and one set makes a negative factor. And that's why the middle terms cancel each other out. So on this next example, I see that it's two terms. I'm going to check to see if it's a difference of squares. It's a difference because of the minus sign. 4z squared is a perfect square. The square root of 4 is 2, and the square root of z squared is z. And 1 is a perfect square. The square root of 1 is 1. So our two factors will be 2z plus 1 and 2z minus 1. Just a little shortcut when you have a difference of squares problem. Just like before, if there is a GCF, you do need to take the GCF out first, even if they are both perfect squares. In this case, though, here's another example. These are both perfect squares and there's no GCF. Square root of 9n squared is 3n. Square root of 16 is 4. That's 3n plus 4, 3n minus 4. But if there would have been GCFs, we would need to factor that out. Okay, last set of examples, more special cases. These are called perfect square trinomials. And if you saw this first one, you may not know that it was a perfect square trinomial just by looking at it. So you would probably set up your parentheses and ask yourself what two numbers multiply to 16 and add to 8. And then you realize, oh, that's 4 and 4. That means my answer is n plus 4 squared. So in some cases, it's not really advantageous to notice that it's a perfect square trinomial. But in cases like the next one, where our numbers are significantly bigger, we would want to check for a perfect square trinomial because it will make our factoring easier. So in this case, I've got 49x squared, negative 70x, and 25. There's no GCF. So if I was using the slip and slide method, I would have to take 49 times 25. And that's huge. So when that happens and you're like, wow, that's going to be a big number, ask yourself, is this a special case? Is 49x squared a perfect square? It is. Square root of 49 is 7. Square root of x squared is x. Is 25 a perfect square? It is. The square root of 25 is 5. But here's how you check it for real. If you multiply these together and double it, it should equal that middle term. So 7x times 5 is 35x. Double it to get 70x. That's what makes this a perfect square trinomial. So our parentheses will be 7x. It'll be a minus 5 because the 70 is negative. squared. 7x minus 5 times 7x minus 5. On the next example, we don't have perfect squares here. However, there is a GCF. And whenever there's a GCF always gets taken out first. That's always, always, always the first step. Don't forget that step. Our GCF in this case is 3. So if I divide all those terms by 3, I get 9x squared, 12x, and 4. Now with what's left, I notice that that first term is a perfect square. That last term is a perfect square. Square root of 4 is 2. And if I multiply these together and double it, I get 12x. So this was a perfect square trinomial.